Hey, welcome to our third video session on the preliminaries review for the flipped classroom for AP Calculus. Today what we want to do is talk about two different things. The first of those things being inverse functions. Let us first define what inverse functions are. Two functions, let's say f of x and g of x, are inverses of one another if their composites are both equal to x. What does that mean? If we take f of g of x, where g of x is the inside function, and g of x, where f of x is the inside function, they both have to come out equal to x. We'll try an example of that in a little bit. Graphically, f of x and g of x would be reflected across the line y equals x. Because really, if you think about it, what you're doing with inverses is you're just switching the x and y components of all the ordered pairs that make up the functions. That means that the range of f of x becomes the domain of g of x, and the domain of f of x becomes the range of g of x. Here's an example. Let's look at the function f of x equals x cubed, and g of x equals the cube root of x. If I take the composite f of g of x, I get x to the 1/3, that quantity cubed, which in fact does equal x. And if I take the other composite, g of f of x, where f of x is the inside function, x cubed, the cube root of that would also equal x. So we would say these two functions are inverses. Graph these two functions on your calculator using y1 and y2 for f of x and g of x respectively, and then also graph a third function, y equals x. What do you notice? Well, what I notice is they are both those functions are mirror images of one another across the line y equals x. So how do you find the inverse of a function? Well, let's take the one we've been working with, x cubed. First thing is I rewrite it as y equals x cubed, solve for y. I get x equals y to the 1/3. I'm going to replace my x with a special notation, f negative 1 of x, which means inverse, and I'll replace y with x. I would then get f negative 1 of x equals x to the 1/3. F negative 1 of x is the notation for the inverse of our original function f of x. Logarithmic and exponential functions. The base A logarithm and exponential function are inverses of one another. These two guys are special functions. The equation for a logarithm is simply y equals log a, which would be the base of x, and the exponential formula would just be y equals a raised to x. These two functions are inverses. This relationship can be used to solve equations when you have an x or a variable as an exponent. We will do that later on, but first we need to talk about properties of logarithms. You may have had this in your trig class or your algebra 2 class, but it's probably a good idea to go over it again. If I have the log of a product, say xy, that can be rewritten as the log of the sum of the individual functions. In other words, the log a of x plus the log a of y. Along those lines, the log of a quotient, x divided by y, can be written as the difference, log a of x minus log a of y. Another very useful rule or property is what we call the power property, and that says log a of x raised to the n power is simply n times log a of x. You can bring that exponent down as a coefficient. Also, another thing that you use a lot of times is the property of inverses, that y equals log a of x can be changed to an exponential form, x equals a to the y, since they are inverses. Keep in mind, however, a, the base, must be greater than 0 and not equal to 1, and x cannot be negative. Why can't x be negative? Well, when you think about it, look at the exponential form, x equals ay. is there any way with a positive base a that I could get a negative number x by raising it to some power y? The answer to that question, people, is no. A special logarithm is the natural log, which is denoted by the equation y equals ln, not LLG, but ln of x. This logarithm is used quite a bit in science and also in finances. Banks use this when they figure interest. The base e is a constant, and it has a value of approximately 2.7. The inverse of this function would be e to the y equals x. Some things that you might need to know is that the natural log of e equals 1 because e to the 1 equals e. Okay, what I'm doing here is I'm just taking that natural log and I'm putting it in the exponent form, and I know that it becomes e to the y equals x, therefore e to the 1 would have to equal e. That's a useful thing to remember, that the natural log of e is 1. Also, another useful equation that we'll use down the road is how to go from log of some other base a, to the natural log. That equation is log base a of x equals the natural log of x divided by the natural log of a. That's worth remembering. Here's a sample problem using logs. Let's say you have a problem that you want to simplify e to the raised to the natural log of 7.2. What I do is I set this equal to some variable. Let's say y. So I have y equals e to the natural log of 7.2. Then I take the natural log of both sides. Remember, whatever you do to one side of an equation, you finish the sentence. So natural log of y then would be equal to the natural log of e raised to the natural log 7.2 power. Okay? Then what I do is I say, okay, wait a minute. That's like the natural log of something raised to the n power, so I can bring that natural log of 7.2 down as a coefficient. So I get the natural log of y equals the natural log of 7.2 times the natural log of e. Well, guess what the natural log of e is equal to, boys and girls? 1. You got it. So now I have the natural log of y equals the natural log of 7.2. So if I'm taking the natural log of two things and those natural logs have to be equal, doesn't y have to equal 7.2? So I could simplify e to the natural log of 7.2 to just 7.2. Here's another one. Okay, again, simplify this. E to the natural log of x minus the natural log of y. In this case, I know ahead that I'm going to choose a different variable. It doesn't matter what variable you want to set it equal to. I choose r. I don't know why I picked r. It just seemed like a good letter at the time. I take the natural log of both sides. Natural log of r equals natural log, in parentheses, e to the natural log of x minus natural log of y. Maybe some of you see where I'm going with this. Notice, I can write the natural log of x minus the natural log of y as a quotient. That's one of the properties of logs. So what I get here is the natural log of r equals the natural log of e raised to the natural log of x over y. Okay? I can now bring that natural log of x over y down because that's an exponent, and I get the natural log of r equals the natural log of xy times the natural log of e. I left that out on the slide. How silly of me. Okay, but what is the natural log of e? Natural log of e is 1. So what I have now is the natural log of r equals the natural log of xy. So therefore, doesn't r have to be equal to x over y? That's the end for this lesson. Check your Google to see what we'll be working on tomorrow, and we will have a short Edmodo quiz. Thanks a lot for listening, and we'll see you for video number 4.